I must express my thankfulness to the organizers, especially to Gerhard, that it is already the second time that I can attend and also speak at this very precious series of conferences. Now, as you say from my title, the dominating expression there is speculation. It means that after decades of speculating on spontaneous collapse theories, I will further speculate, and I have a special excuse this time that the tests which may follow from my new speculations, I mean, these tests look quite robust and feasible. So let's see how we come to those tests after some speculations, admittedly. I have only few transparencies with very few texts and with some figures. And as always, we start from the quantum classical boundary issue, which issue had not been existed in the early days of quantum mechanics because people didn't apply it, but to microscopic systems. Whenever you realize that your quantum theory is a candidate to be the top priority theory of physics, you extend it for macroscopic systems as well, and you face problems. It turns out that massive degrees of freedom matter, so I'm going to concentrate on the quantum dynamics of massive degrees of freedom, which are the hydrodynamic degrees of freedom. And in the simplest case of a single massive degree of freedom, I will consider a single massive spherical object, and I will concentrate on its Schrödinger equation, on the Schrödinger evolution of the center of mass wave function. Oh, sorry. Okay. As you say, if I start from a decently localized center of mass wave function, usually it expands and expands and expands without limitation. Now, when the extension of the wave function is too big, when it is macroscopic, we call the state the Schrödinger cat, and we don't really like them. This is an ideal case when the macroscopic center of mass is so to be isolated from the environment. Now, let us consider a more realistic situation when there are light degrees of freedom, maybe light particles, literally taken as light quanta, or any other environmental degrees of freedom which are not massive, like ambient gas or even any other light. The important distinction between center of mass and environment is the center of mass is the center of mass of the massive object, and any other degrees of freedom shouldn't represent too much masses. Now, if you calculate the Schrödinger evolution, the unitary evolution of this composite wave function, you will realize that basically the expansion of the center of mass looks like before. of course, the composite wave function becomes a huge entangled function where entanglement has been created between the center of mass and the rest of the light degrees of freedom. But anyway, as a matter of fact, the mass of the large body, of the massive body, will dynamically dominate the expansion of the wave function. So we have the same situation. We have the same more realistic Schrödinger cat. It is happily there despite the environment. We are not too happy with them because Schrödinger cats are problematic, and different authors, and even the same author used to present different and changing controversies about the Schrödinger cat. Now, it is now well known that one way to suppress or even eliminate the Schrödinger cat states from standard quantum mechanics can be done by the so-called spontaneous collapse models. There are too many popular spontaneous collapse models. The GRW, the DP, where P is Raja Penrose and T is myself, the CSL model, all of them can be taught an easy way just by claiming that they are universal von Neumann standard measurements with two footnotes. The measuring devices are present everywhere and every time. They fill in the whole universe, but the devices are hidden. They influence, they change the unitarity of our quantum mechanics, as usual von Neumann measurement devices used to change, but the devices themselves are hidden. So this is the shortest way to teach the essence of spontaneous collapse theories. Now the DP is special because this hidden, continuous monitoring by the hidden devices refers to the mass distribution presented by the quantized system. And this monitoring, this universal von Neumann measurement is a weak measurement, and the strength is proportional to the Newton constant. Therefore, I used to call the DP model as the G, or gravity-related spontaneous collapse model. And as a result of mass distribution monitoring, the main result of the DP modification of quantum mechanics, that it will collapse the massive degrees of freedom. It will disentangle the massive degrees of freedom. It is visualized here that you start from a localized wave function, it expands, but before it grows into the Schrödinger cat, it is localized. So this second arrow stands for the DP collapse. Now, there are detailed analytic models to describe this cycle of expansion and localization. And there is a regime where the unitary spread and the DP collapse are balanced. It is the natural situation. So if you calculate this equilibrium, this balanced situation, where all massive degrees of freedom have some natural localization, You can calculate the equilibrium collapse rate, and in one version of the DP model, it equals to this quantity where rho nuclear is the nuclear mass density, 10 to the 12 gram per cubic centimeter. And it turns out to be 1/millisecond. And this time scale will be referred to by tau g. Tau g is 1 millisecond, and it is the time scale of equilibrium dP, or gravity-related collapse rate. Now, here you see the unitary standard quantum mechanics as it evolves the massive wave function into a Schrödinger cat, and you see the result of the dP collapse modified quantum mechanics. Now, unfortunately, and this is valid for all spontaneous collapse theories, the difference between this state and that state is not measurable. I mean, the spontaneous collapse is never detectable, because to detect the collapse, to discriminate between this state and that state, you should be able to detect all the environmental light particles. And it is impossible, and therefore you can only detect a few of them, or basically you can detect the center of mass of the main object, and the behavior of the center of mass is the same in quantum mechanics and in the dP modified quantum mechanics because due to the huge and overwhelming decoherence effect of the environment. Now, there are experiments planned and even running experiments where people try to isolate the massive degrees of freedom from the rest of the world, and in that case, they may be, in these experiments, in some years or maybe in 20 years, we are not sure about it, we can be able to detect the decoherence effect of the spontaneous collapse theories, including the dP collapse theory. But it is a very, very long run. As I mentioned, it may be 1 year or maybe 20 years that we can reach the first significant results to confirm or to refute the spontaneous collapse, the competitive, otherwise competitive spontaneous collapse models. Now, I tried to do something better. And it is that I extend the dP theory to associate the collapse with something which is detectable. So let us associate this collapse step with something which is detectable. Not only that we can detect the additional decoherence caused by this collapse on the top of the environmental decoherence, we need some real effect which comes from collapse itself. And I supposed that the Newton force is generated by the dP collapse. In other words, that if there were no dP collapses, there would be no Newton force around the object. So this is a very, very vague, so radical new assumption. And let me see. So we carry on but a single number from the collapse theories to the realm of Newton gravity. Read, please, together with me. The Newton forces emerges from disentanglement at the disentanglement rate, which is 1 over millisecond. If the Newton field emerges as a consequence of disentanglement, which is disentanglement means collapse. So if Newton field emerges because of the collapse, then it must have an emergence time, and it should be the same, 1 millisecond. Of course, I have been discussing with myself this issue for decades. I failed to get any detailed analytic models for this step. But if we don't have any analytical tool, still we can construct a minimum heuristic extension of the Newton equation to generate the Newton potential. Look at this equation. It contains a simple delay time, a delay mechanism compared to the instantaneous Newton rule. Now, in order, if you just make this ansatz, you will immediately realize that it is not boost invariant. It gives you a boost dependent Newton field, but it is easy to correct if you claim that this expression for the Newton field should be evaluated in the co-moving, free-falling reference frame, where the instantaneous velocity of the object is 0, and where the instantaneous forces are non-gravitational forces. If as a result, you get a very favorable feature of this ansatz. If all forces are gravitational forces, then you arrive back to the Newton gravity. Then the delay cancels. So Newton law is restored in absence of non-gravitational forces. On the other hand, if we have some non-gravitational forces, we have several fine, nice, even robust effects, maybe easily testable. The first effect is a universal effect in the Earth field. If we have a free-falling object, then there are no non-gravitational forces upon it, so it creates its standard co-moving Newton field, 1 over r, and it is instantaneous. On the contrary, if you consider static objects, suspended or supported, then since the Newton field should be the delayed field, delayed by 1 millisecond, and calculated in the free-falling co-moving system, these guys would show up a bit upper than their geometric position. So they create a field from a position a bit upper than they are. And this distance is quite big. It's the standard Earth's standard acceleration g times 1 millisecond squared, and it's 10 to the minus 3 centimeter. I have two other effects to show you. This is a similar effect. Here, the effect is small. And as you see, I present a massive object which is revolving on a rope. So it is under some non-gravitational force because of the rope. It is accelerating again. Its effective position is a bit closer to the center than its geometric position. Therefore, the gravitational force of this object is different from the standard one. I calculated it for the center of the orbit, and there is an enhancement factor which is at the bottom line, and it is valid if the revolution frequency is much smaller than the scale of the emergence time, which is 1 kilohertz. And how much time do I have?
10 minutes.
10 minutes, perfect. And this is, you might have asked me, where's the delay? If I'm talking about a delayed emergence of Newtonian gravity, where's the delay? Now, there is delay, a large delay effect, if you exert some robust sudden force, some sudden impulse on your would-be Schrödinger cat, or wouldn't be Schrödinger cat. So if you have a static source at the beginning with its standard Newton field around, and you displace it suddenly, you need some much bigger non-gravitational force to do so. I mean, bigger than in the previous examples. So you displace it suddenly compared to the one millisecond time scale. Then I'm sorry to claim it is quite mysterious consequence of the modified Newton equation, but the Newton field remains around the original position for 1 millisecond. And according to an exponential law, of course, it will be damped at the empty position, and it will grow up around the new position. I don't think that this experiment can be performed with robust big objects. But if people are able to detect gravitation for not just for non-objects, but for say objects of 1 millimeter, 1 centimeter. In that case, for a 1 centimeter object can be displaced on a time scale which is shorter than 1 millisecond. So I think that all three examples show up as some provoking feasible tests. And I must say that I'm not expert at all in the field how Cavendish and modern Cavendish experiments are able to calculate the gravitational force up to the 5th or 6th digits. There is a painful failure, you know, to measure the Newton constant. It is not known better than 6 digits or 5th, maybe 6 digits. 5th, thank you. Thank you. No, I don't mean that these effects might have jeopardized the precision of the past Cavendish experiments. But at least I mean that I haven't discovered any currently available experiments that would deny that would immediately disclose my proposal for a 1 millisecond delay, 1 millisecond laziness. It means that the time, the time resolution of the standard Cavendish experiment is half an hour, or so. It is. There may be a window which hasn't been opened so far. And this is a window to discover Newton gravity at a higher resolution, higher time resolution, sorry. So that's the summary. You don't see anything new, just a picture how out of the collapse, the Newton field is supposed to emerge. This is the upper picture. And the lower picture is 3 figures of the 3 different experimental testable proposals. Thank you.
At the beginning, you said that the standard collapse models, you cannot test them. You have made the statement like in principle, no?
No.
You cannot test the gravitational effect.
No. You cannot test the collapse. You can test the decoherence effect of the collapse.
Okay.
Only the decoherence can be tested if you suppress the environmental decoherence.
Because I wanted to call attention
but
that the model can have other implications that you can test.
Yes, because I created a concept that the collapse is responsible for the Newton gravity. So this is a trick. Otherwise, you don't see the collapse, just the decoherence. You don't see the disentanglement. We talk about it.
The next question, Phil.
Yes, we have solved this explicit model for quantum measurement by defining the Hamiltonian for the apparatus and then looking at the common evolution of the tested system and the apparatus together. We find there that the collapse happens automatically. So what would you want to say about this situation? Would you like to add your type of collapse to this as well?
Sure, but I must contradict you. Let me ask you, have you ever left unitary quantum mechanics? Certainly not, have not. So if you have a pure state initially, whatever complex system you are calculating, it remains in a pure state. There is no collapse. There is decoherence.
No, the point is, for a realistic apparatus, the apparatus itself must start in a mixed state.
Yeah.
You cannot get a macroscopic system into a pure state. So your total system starts out in a mixed state, even if your tested system is in a pure state. And unitary evolution will bring you from one mixed state to another mixed state. Yes. There's no unitarity paradox.
If the evolution is unitary, you don't see collapse. That's...
It happens, it's there.
So do you envisage this in an accelerating frame? Sorry. Do you envisage this kind of experiment being taking place in an accelerating frame? Or is it a linear motion? Because you were talking about your system moving.
Yeah.
Yeah, so
but
is it accelerating or is it running at a constant velocity?
you must accelerate it by some non-gravitational force.
So it's the acceleration.
Yeah.
Right, okay. Because, I mean, do we really understand accelerating frames as well enough or be able to do that to try and test this kind of system?
Sorry, say it again.
Well, accelerating frames are pretty renowned for being tricky objects to deal with, experimentally speaking.
Yeah.
And I'm just wondering, sorry? Well, you know, all sorts of reasons. And so to try and do this kind of experiment would be, you know, to try and extricate from the background, as it were, it would be incredibly difficult, I would suggest. Anyway, just a comment.
Can you remind me again why it should be exactly the millisecond time scale? Shouldn't that scale with the mass?
Yeah. According to this DP concept of collapse, if the center of mass extends so much that the mass distribution, and here I mean the microscopic mass distribution of the object, differs too much from in the left-hand side and on the right-hand side of the COM position. It means that, say, you have a crystal ball, and you displace it so that the nuclei won't overlap anymore. Then the collapse must be very strong and immediate. So if the nuclei are going not to overlap because of the spread of the center of mass, the quantum mechanical spread of the center of mass, then according to the DP model, you have to act. You have to impose a collapse and relocalize the center of mass in a narrow region, so that the nuclei shouldn't extend more than their size, than the nuclear size. And if you calculate the rate, you can get this 1 millisecond in 2 lines.